Okay, so in this video, we're going to be looking at derivatives part 2, the chain rule. This is a very important rule that we want to make sure we follow. Okay, it's on every derivative you ever take. So the chain rule is applied all the time. Just going to get a quick focus there. So here are some rules that we're going to use. These are the derivative rules. And again, this is the rule you want to memorize. It is based off the chain rule. Okay, and we'll look at these, and then we'll go from and show you how the chain rule works and a bunch of other things. So the chain rule says that if u is a differentiable function with respect to the variable x, notice there's no x in there, but you can see. So u is some function of x. We're taking the derivative of this with respect to x, and so this is the derivative of the function right there, and then this part is what the chain rule talks about. This is the derivative of that function of x. So that's the chain rule, so that you have to take the derivative of the inside function also. Okay, so these rules right here are the trig rules that you're going to also need to memorize. Here's the exponential and log rules. And a is a real number, so when you see the a, it means it's a real number. Okay, so let me move this out of the way. It looks like it's in the way on my end. So here's the exponential and logarithmic rules. So e to the u is its own derivative, so it's very easy to remember. And then you have to take the derivative of that u function with respect to x. The natural log, very simple, it's 1 over whatever u is, and then times the derivative of u. Sometimes you'll see this as u prime over u. And here is the exponentials and logs that are not base e. So a to the u, you'll notice it's exactly the same as what it was for e, except you have to put on this natural log of a, whatever the base number is, you have to take the natural log of it and times it. And the reason why this one does the same thing, except the natural log of base e is just 1. That's why you don't see it over here. It's there, you just don't see it because it's a 1 in both of these cases. So in the exponential, you're going to multiply by the natural log of a. For the logarithmic, you're going to divide by the natural log of a. So let's look at some problems with the chain rule itself. So the chain rule is based off the composite functions, f of g of x, where I have an inside function and an outside function. Okay? So we need to identify both the inside function and the outside function. Usually the inside function is in the parentheses or inside a symbol where the parentheses are implied. So I think I have an example here we're going to do. Let's take a look at this one. So here's a problem right here. I'll zoom back out here in just a minute. Identify if the function is composite. If it is, identify the inner and the outer. So it's very important that we can do this, because this is what's going to lead us to making sure we do the chain rule properly. So usually what I tell everybody is, do you see a parentheses? And in the first one here, I don't see any parentheses. Parentheses are usually a giveaway for the chain rule and composite function. There's nothing here, so there's no really inside function itself. So this one is just a polynomial. It is not a composite, so that is a no. Okay? When I come down here and I have this e to the 3x, we need to remember that exponents are always in parentheses. It's an implied parenthesis, even though you don't see it. Okay? So that means, because this is not a single variable only, there's something else with it, then this right here is the inside function. So this one is composite, and the inside function is 3x, and the outside function is e. And you just, we call it e to the u. Let's put it that way. So replace everything in the parentheses with a u. Okay? Coming over to this one, we can see parentheses are involved. When you have parentheses, it's almost a dead giveaway that the inside will be everything that's in the parentheses, x to the third plus 5x. That's the inside function. And the outside function is, if I replace everything inside with a u, then this is just u squared. That's the outside function, u squared. Here, again, parentheses. All trig functions are the parentheses part, the argument part. If there's something other than a single x in there, then it is the inside function. Even the inside x is the inside, because the derivative of x is just 1. So the inside is going to be x squared, and the outside is the sine, and then the u. Okay? And then the last one I have over here is this one. Is this right here a composite function? And the answer to this would be no. This is not a composite function because this is just a number, 3. This is a variable being times to something else. Even this is not considered a composite function because this is just a singleton x. If it was anything other than the x, then it would be considered a composite function. So this right here would be a no. And so that's how those work. Okay? So let's take a look at some more information about this. And I'll pause it right here if you wanted to see my internal notes and stuff like that. So let's look at the chain rule name, how this works. Let u be a differentiable function with respect to the variable x. And so I'm taking the derivative of an outside function and an inside function. Okay. So the derivative is this. You take the derivative of the outside function, and you'll notice that the inside stays the same. You're not doing anything to that. So you're taking the derivative of the outside function. Okay. So in this case right here, we would take the derivative of e to the u. Okay. And you would get whatever u is, you're going to rewrite it. And then you're going to times it by the derivative of the inside function with respect to x. So in this case, then I would be taking the derivative of 3 to the 3x. That's what goes there. And sometimes there's even an inside function there. So sometimes you can have a function inside, another function. And so this du, just make sure that we just keep on doing the chain rule, keep on taking the derivative further and further inside until we have completed the derivative all the way in. Until the last thing is there's just a single x in there. And I'll show you some examples on this so you can see how this works. But that is the chain rule. It is probably the most important derivative rule because it is in every derivative problem. You were actually using it already. You just didn't know what it was called while you were using it. Okay? When you wrote that dx down, that turned into a 1, that was the chain rule we were doing. Okay? So let's look at the next one. And I have some examples. And we're going to do some derivatives of these things. So we're just going to do a bunch of derivatives now. Okay? Find the derivative of each one. So here we go. Here's y. I want to find, and I can call this dy dx, or I can call it y prime. I prefer dy dx, but you can put a y prime if you want. So the derivative of this is this. The derivative of this is, so the outside function is something to the 4th power. Something to the 4th power. So the derivative is the derivative of that something to the 4th. So what is the derivative of u to the 4th? It's going to be 4. And then you take the stuff that's inside the parentheses, because we're not changing that yet, and that lower the power by 1. See? So u to the 4th, okay, that's the outside function derivative. Times. Now ignore everything outside and only focus on the inside stuff and take its derivative. When I do this, I always use a square bracket to indicate that I'm now taking the derivative of something like the inside. So what is the derivative of this? Okay, well, that's going to be a 3x, lower the power by 1. Okay, and then, because that's already an x, but technically by chain rule, that would be a dx. dx. Take the derivative of the x with respect to x. And that's how you kind of know that you're done. What's the derivative of this side? Well, it's going to be 5 dx dx. That was the inside function. That is the derivative. Okay? The dx dx's turn into 1s. And what you have here, you're done. You don't necessarily need to multiply it out in violent terms unless it's beneficial to do so. Okay? So the final response here for dy dx would be 4 times x to the third plus 5x times 3x squared plus 5. So that would be your derivative right there. What about this when I have a root? Before you take any derivative, if there's roots involved, you should rewrite them in fractional exponent form so that you can use the power rule for it. So you should rewrite this as h of x raised to the 1/3 power. And when I do that, I see that this is the inside function, and the outside function is a power rule, u to the 1/3. So what is y prime going to be? Outside derivative, so 1/3. All this stuff inside, don't even worry what it is, just rewrite it and lower the power by 1. So 1/3 minus 1, negative 2/3. And now I'm going to take the derivative of the inside with respect to x. So the derivative of h is h prime of x times, and then the derivative, since it has a parenthesis, the derivative of the inside of that, which is dx dx. And so that is my derivative there. And again, if I clean this up, and I can't, but I'm not going to go any farther than that, this turns into a 1. So you would not write this after this step. Over here, y prime equals the derivative of an exponential to a power is its own derivative. So this is e to the 3x times, now I got to do the chain rule, which is the derivative of the exponent. The derivative of 3x is 3 dx dx. And there you go. So as we get moving along, we usually do not do the dx dx anymore. But just know that it is there. So I'm probably from this point forward not going to write the dx dx unless it's in a function notation format like this. So let's take a look at this one. This is the natural log. So y prime. So the derivative of that is you take this quantity right here, and it's 1 over that. So there's that, times the derivative of the stuff in the parentheses. And the derivative of that is simply 5. dx dx, which I'm not going to write because it's a 1. And then I can rewrite this in the final format of 5 over 5x plus 1. So that would be the derivative of that. Let's look at this example right here. Y prime equals, this is e to some power. So then the derivative of that is e to that same power. You don't do anything to it. You just rewrite it. Times, and now I do the derivative of the inside function. So we would use the derivative of the sine, which you're going to have memorized, which would be the derivative of sine is the cosine of x dx dx, because that's the inside there. Remember, there's parentheses right there. So dx dx. Minus the derivative of that would be 3 dx dx, which I'm not going to write because it's a 1. Okay? And there you go. That's the derivative. This one has a bunch of function notation. So when I do function notation of stuff, I am going to use the dx dx at the end. So this is the derivative of y with respect to x equals. I have to identify the outside function. So you can see that I have 2 insides. This is an outside function of everything in there. G is the outside function of everything in there. And h is the outside function of everything in there. So we see that we have a bunch of nesting going on. So let's start with the outside. This is the parenthesis for the outside. It doesn't matter what's on the inside, it's just going to get repeated. So this is the derivative of f okay, of all of this. And 1. And then by the chain rule now, I have to go on the inside of that, and I'm going to take the derivative of this, which by itself is a chain rule action. So the derivative of this outside function is g prime of all of that times the derivative of inside that one, which in this case is going to be h prime of x times the derivative of inside of that one, which is dx dx. This is how you kind of follow a nesting format. Okay? Farther and farther in. Outside, working your way into all the parentheses going inside, nested out. Okay? Here's a one over here. A technique for this problem right here is you also want to rewrite these. Any trig to a power like this, where it's above the trig function, not above this, but above the trig function, you want to rewrite. Okay? Very important that you do so because you don't see it. It's very difficult to see it properly here. This is the sine of 7x raised to the third power like that. So this helps you see the nesting and the inner and outer function much better. Okay, so any power of a trig function you want to rewrite like this. You always want to think about it that way. So then y prime becomes, this is something to a 3, so u to the third, so this is going to be a 3, all of that. Lower the power by 1. Now the derivative of the inside here times, so we got to take the derivative of the sine function. The derivative of the sine function is the cosine function, which is the cosine of that quantity. It doesn't change. Okay, so the derivative of the sine is the cosine, and then I have to times it by the derivative inside of that, which is the 7x. So now I have a derivative of 7 dx dx. So you see we had a nesting here also, because we had this outside was u, the inside was sine, the inside of that was 7x. So the outside, the derivative of the inside function, and then the derivative inside those parentheses that it had. That is the chain rule. Okay. The secant over here. So the derivative of the secant is secant times tangent. So this is the argument here. So when you rewrite this, this would be the secant of 2x times the tangent of 2x times, and then we have the inside function of 2x, which would be 2 dx dx. So that would be the derivative there. And then as you do your final writing of it, this 2 will move out to the front because it's a constant, and dx dx goes away. That's 1. So there's how that works. Okay, this is all those derivatives here. Let me zoom it out just a bit, make sure you can see them all. Actually, I'll just give you the final version over here. So if I had any side notes, you can write them down also. So just take a moment here, pause it, zoom in and see if you can see anything that I've written there that you can add to your notes. Okay, so I have another example. Right there. Go with the table. So this may be a look that you might see on a test of some fashion. Okay. The functions f and g are differentiable for all values of x. The table gives selected values for the function f and g and their derivatives at selected values of x. So when x is 1, f of x is that, f prime is that, g is that, g prime is that, and so forth. Okay. So then they want you to come over here and find the derivative of h with respect to 1, okay, at 1, and h is this function right here. Okay, so what should I do for this problem? Well, the first thing I should do is figure out what is h prime. The last thing you're going to do is figure out what that is at 1. Okay, so we don't do it all at 1. We don't do the 1. We do the derivative first, and then we'll plug in 1. That's what we're going to do. So what is h prime of x? Well, The outside function is cosine. The inside function is f of x. Doesn't matter. Let's go for it. Here we go. So, what is the derivative of the cosine of the cosine function? If you go, remember, look at your notes, it is a negative sine. So the derivative of the cosine is negative sine of whatever this was. Times, now I need to do the chain rule and do the derivative of the inside, which is f prime of x, and then times dx dx, which I'm not going to put in there. That is h prime of x. So once I have that, then now I can find h prime at 1 by simply plugging in 1 to all of those x's. And then this is f prime at 1. And so we can now go to our table and we can plug in the values we know. So this is minus the sine f1. F at 1 is pi over 6. And f prime at 1, excuse me, I should just write what it is. F prime at 1 is 4 times the square root of 3. And then I can clean this up because I can figure out the sine of pi over 6 because we remember our unit circle. I don't know why I have a k. So h prime at 1 is going to be a negative 1/2, which is what that is, times 4 times the square root of 3, which gives me a final number of negative 2 times the square root of 3. And there is h prime at 1. Okay. Same thing for this problem right here. What is k prime at 2 if k is equal to that quantity of that function right there? So then what is k prime of x? Well, it's e to the g of x, because e is its own derivative, times the derivative of that, which is g prime of x, times the derivative of that, which is dx dx, and so I don't need to write it. And then we just go the same process we did, plug in 2. So this is e g of 2 times g prime of 2. And then g of 2, g at 2 is 8. So this is e to the 8. G prime at 2 is 5. So this is times 5, which gives me 5e to the 8. Done. Okay. Here's a graphical way they might ask you to find derivatives. So the graphs of h and m are shown. H is the solid one, m is the dotted one, so you can see it. Okay. There's some various numbers on here. These are all line segments. P of x is m of h of x. And so what is p prime at 1? So to do that, we have to first find p prime. This is the chain rule, so it is the derivative of m at h of x times, now the derivative of the inside function, which is h prime of x dx dx, because you take the derivative of that part in there too, which is just dx dx. So there is my derivative. So what is p prime at 1? It is m prime at h of 1 times h prime at 1. Okay, so the thing to remember here is, what is a derivative? To find these values from here, I have to understand what a derivative is. Remember, a derivative is a slope of a tangent to the curve. And in all these examples over here, each of the pieces of the curve is a straight line. Okay, it's a line segment. Meaning, no matter where I pick on this part right here, from here to here, the slope is identical. It's the same slope because it's its line segment. So every segment has the same slope as every other point on that segment piece. So to do this problem, what I need to do is go look at these functions at 1. Okay? So what is h at 1? This is an actual point that you're doing here first. This inside here is not a derivative. It is a value. h at 1, okay, and I come over here, h of 1, h is the solid one, at 1 is a 3. I know it's hard to see there, but it's at 1, 3. So when h is 1, at 1, h is 3. So this is now going to be m prime at 3. And then h prime at 1. Now both of these now are slopes at a particular x value. So let's go find out what the slope is at these. And you can do them off to the side, however you want to do them. Doesn't matter to me. It depends on how you look at it. 1 is on this segment right here on H. So what is the slope of the segment? Well, it's negative. I can see it's negative. You can do the slope formula or whatever you want to do. I can do rise over run. The slope is negative, so I'm going to go down 6 and over 2. So H prime of 1 is the change in the y's. Change in the x's, negative 3. And m at 3, here's 3. So the slope of m at 3, there's no value here, but I can see that I'm on this segment here for m, so it's the same slope as that. And so that is also a negative slope. I'm going from here to here, so the change in the y values is I'm going down 1, and then I'm going over 3. So down 1 over 3, and I have a slope of a negative 1/3. So then I take these numbers and plug them in here. I got a negative 1/3. I have a negative 3. And so P prime at 1 is 1. And there you go. So that's how I can use that information and the chain rule to help me find values of different derivatives. So that ends the second video.